Welcome to The Explainer. Today, we are diving headfirst into a real technical detective story. Now, if you're a water treatment engineer, or honestly anyone who works around industrial plant operations, you already know that a high-rate solid contact clarifier, the HRSCC, is basically the beating heart of your water treatment process. But what exactly do you do when that heart starts beating out of rhythm? You know, when it starts behaving in a way that just defies all basic logic. What happens when the chemicals you pour in seem to literally vanish, only to magically reappear exactly where they shouldn't? Well, today we're going to crack a bizarre clarifier anomaly that has left plenty of seasoned operators scratching their heads.
So, here is our roadmap to solve this crazy failure. First, we'll outline the HRSCC mystery itself. Second, we'll dig into exactly why chemical mixing fails. Third, we'll explain the filter effect, and finally, we'll walk through a rock-solid 4-step plan to actually fix it.
All right, part 1, the HRSCC mystery.
Okay, picture this. You're dealing with incredibly high inlet water hardness. We're talking somewhere around 2,000 to 2,600 parts per million. Naturally, you're pumping massive amounts of lime into your system to soften it up. But here is where the headache begins. Your center well, which is exactly where the raw water and chemicals first meet, is registering a highly acidic pH of 4. Yet somehow the treated water at the overflow is sitting at a heavily alkaline pH of 11. Under normal design conditions, that center well should absolutely be sitting at a pH of 10 to 11. Instead, your center is acidic and your exit is basic. How is that even physically possible?
Well, fundamentally, your system has completely abandoned its design intent. Think about it. You paid for an active, highly turbulent mixing tank, but your current reality? It's basically functioning as a giant line bed filter. Instead of fiercely blending those chemicals into the incoming water, your clarifier is essentially just dropping them straight to the floor and using them as a giant static filter. To actually fix this, we need to understand exactly why this transformation happened in the first place.
Which brings us to part 2, why chemical mixing fails.
The secret here actually lies in the sheer weight difference between your materials. Standard water has a density of 1.0 grams per cubic centimeter. But hydrated lime, that clocks in at 2.2 to 2.3. It is literally more than twice as heavy as the water it's entering. Because of this massive density gap, hydrated lime just doesn't dissolve instantly on contact. It wants to sink, and it wants to sink fast. To really wrap our heads around this, think of it like the sugar grass effect. Imagine dropping 4 heavy spoonfuls of sugar into a glass of ice-cold water without stirring it at all. What happens? That heavy sugar sinks like a stone straight to the bottom. If you take a sip from the top of the glass, which, by the way, perfectly represents your clarifier center well, it tastes completely bland, or in our plant's case, it remains at that acidic pH of 4. But the very bottom of that glass, that's going to be incredibly sweet.
So, how do we stop the chemicals from plummeting to the floor? It all comes down to a really crucial concept called the G value, or velocity gradient. This is basically the raw measure of mixing power in water treatment. Flash mixing requires a phenomenally high G value. You need intense mechanical turbulence to literally tear those heavy chemical particles apart and violently force them into solution with the water before gravity has a chance to pull them down.
If your center well turbine is failing to create that proper aggressive vortex, you experience what we call the washing machine effect. Imagine your washing machine agitating at a painfully slow speed. The heavy laundry detergent just drops to the bottom and stays trapped under all the clothes, while the water at the top stays completely clear and unmixed. In your clarifier, a slow agitator means that heavy, dense lime simply drops to the bottom like a rock, completely bypassing the incoming water.
Let's move into part 3, the filter effect explained.
Okay, so we know exactly why the center well is acidic. The lime sank. But how on earth is the overflow water magically reaching a pH of 11? Well, all that heavy unmixed lime doesn't just disappear into the void. Because it's twice as heavy as water, it accumulates into a massive, highly alkaline sludge blanket sitting right at the bottom of your clarifier's bed. We're talking about a thick, dense layer of pure, unreacted chemical with a staggering pH of around 14 just chilling at the floor of your tank.
Now, combine that highly reactive sludge blanket with the physical flow pattern of your clarifier. The HRSCC operates on a V-shaped flow pattern. The raw, acidic water is violently forced down through the center well. Once it hits the bottom, it has to make a U-turn and travel all the way up through the massive outer zone to eventually escape at the top overflow weir.
And this perfectly, brilliantly illustrates the teabag effect. Remember that highly acidic pH 4 water plunging down the center well?
Well, acidic water happens to be the absolute perfect solvent for lime. As that clear, acidic water reaches the bottom, it's forced to literally push its way through that dense, pH 14 sludge blanket we just talked about. Just like hot water pouring over a tea bag extracts all the tea's color and flavor, the acidic downflow water strips the powerful alkali right out of the unreacted lime bed as it passes through. By the time that water rises back up to the overflow, it has been perfectly brewed into a highly basic pH 11 liquid. Mystery solved.
All right, part 4. 4 steps to fix it. Enough theory, let's talk solutions. Here is your 4-step battle plan to destroy the teabag effect, pull that old heavy sludge out, and perfectly blend your new lime. We're going to tackle agitator speed, dosing location, sludge blowdown, and slurry concentration. Step 1 is all about unleashing maximum turbulence. Check your VFD settings for the center well agitator immediately. Honestly, you might just need to crank the speed up. If that doesn't do the trick, inspect the gearbox for mechanical failure, but most importantly, perform a visual turbulence test, what operators often call the Balti test or bucket test. When you look down into that center well, you absolutely must see a visible vortex, a real whirlpool. If the surface water looks calm, your mixing power is basically zero, and that agitator needs to be adjusted right now. Step 2 is a classic plant workaround, a really clever jugad. If your lime dosing pipe is lazily dropping chemicals into a calm dead zone, move it. Temporarily extend the dosing pipe so that it feeds directly over the agitator impeller's high turbulence suction zone. By forcing the heavy lime directly into the chopping blades of the mixer, you literally guarantee it gets shredded into the water. If you execute this right, you should see the center well pH jump right back to normal within an hour. Step 3, you have got to eliminate that old filter bed. You must flush out the unreacted lime that's currently hoarding the bottom by frequently opening the bottom desledging or blowdown valve. To actually know when you are done, perform a sludge volume index check. Take some water from the bottom of the outer zone in a 1-liter measuring cylinder. If you see the sludge settling incredibly fast and looking heavy, it means that old, unreacted lime is still trapped in your system. Keep flushing until it clears up.
Finally, step 4 actually happens before the chemical even reaches the clarifier. Make absolutely sure you aren't dosing a thick, heavy lime paste. Dilute the slurry in your dosing tank and definitely ensure the dosing tank stir is running continuously. The lime needs to be thoroughly broken down and perfectly suspended in liquid before it ever hits the dosing pump. This gives your center well agitator a much easier job. And that brings us to the end of our investigation. I want to leave you with one final provocative thought to take straight back to your plant today. Right now, is your clarifier genuinely acting as an active dynamic mixing tank? Or is it secretly just a giant teabag? Don't guess. Go check your agitator speed today. Thanks for joining me on this explainer, and keep questioning how your systems really work.